Good afternoon, and thank you for attending the Steel Joist Institute's webinar, New Methods for Ponding Analysis of Open Web Steel Joist Roofs. My name is Tia, and I will be moderating today's webinar. Today's presenters are Dr. James Fisher and Mark Denovit. For today's webinar, will include 1. Recall the roof ponding requirements within ASCE 7, IBC, and FM Global. 2. Describe the limitations of the method of ponding analysis given in Appendix 2 of the AISC Specification. 3. Investigate the stability of simple roof systems for ponding using the SJI Roof Bay Analysis tool. And then lastly, identify the main factors influencing the ponding stability of open web steel joist roofs. We will now begin today's webinar, New Methods for Ponding Analysis of Open Web Steel Joist Roofs.
As Tia said, you have two presenters today, myself, Jim Fisher, and I'm going to review ponding requirements and also give an introduction to the SJI Roof Bay Analysis tool. And then I'll be followed by Dr. Denovit on the direct analysis method for ponding, which Mark developed for the spreadsheet. And it's also making use of the roof bay analysis tool to evaluate those bays in a building that are susceptible to ponding analysis. So I'll be taking over first, and then we'll switch to Mark Denovit after my portion. This is simply a slide that I took a few years ago. It's just standing water, and there's a bunch of leaves on top, and I thought to myself, boy, we're really asking for a ponding stability problem here, because very likely the roof drains are not working, and I didn't see any secondary drainage system. But as far as I know, on that particular building, nothing bad happened, but let's hope that was the case. But that's, ponding, as we're talking about, is for stability of the roof. It's a stiffness requirement mainly, and a strength requirement. I should mention that there is a brand new, a second edition of the SJI Technical Digest No. 3, which is the structural design of steel joist roofs to resist ponding loads. And that you can see the date on there is February 2018. You can order the hard copy of this document. I believe it's about 90 pages from the Steel Joist Institute, steeljoist.org, for $25. And sort of like the TV commercials here, if you order today, no, you don't have to order it today, but if you download, which we'll talk about a little bit later, the ponding tool, you can also receive a PDF of Technical Digest No. 3 for free. So if you want a hard copy, go to the SJI website and order it. If you're happy with the PDF, simply order the tool. Okay. First thing I'm going to do is have some comments on IBC requirements, ASCE 7 requirements, FM Global, and then a few comments on a number of comments on AISC 360, our new specification, and also a comment or two on the SJI requirements relative to roof ponding. Let's start with the International Building Code, and please forgive me, a lot of this information is just reference material, so it's not real sexy, to just read this stuff, but I'm going to point out the highlights of a lot of the criteria. It's sort of like reading specifications, but it's all necessary for you to understand what the various building codes say about ponding. And some of this you may already know. If not, it's a excellent refresher, certainly. IBC indicates that design and installation of roof drainage systems shall comply with sections in the IBC and also the International Plumbing Code. 1503.4.1 says basically that you need to have emergency overflow or secondary drains. It is a requirement, and it's where roof drains are required. It says secondary roof drains or scuppers shall be provided when the roof perimeter construction extends above the roof that will cause water to be entrapped. What that means certainly is that if you had a roof system that had simply gutters, no parapets, and the water can just run off the roof without being entrapped, then you would not need any sort of secondary drainage system. Some of the things I've put in red on the slides I think are kind of important words. If the primary drains allow buildup. And basically you'll see that most of the items in the codes and ASCE 7 say that one must consider that the primary drainage system is blocked, and that's why you need the secondary system. IBC also says that scuppers can be used certainly for the secondary drainage. They must be sized to prevent the depth of ponding water from exceeding that for which the roof was designed. So certainly they're indicating that you have to design for ponded water. It also says scuppers shall not have an opening dimension less than 4 inches. Seems pretty small to me. Most architects would say if they want to look at the side of your building, they hate to see the little openings in it that may have scuppers in a precast or a tilt-up wall. But my viewpoint is that they should be as big as they can be, because that is what's going to let the water off the roof. So anyway, that's a minimum size. 1507.10 on built-up roofs must comply with section 1507.10. And here's one that some engineers are still missing. Some architects are missing it. It says built-up roofs shall have a design slope of a minimum of not less than 1/4 vertical to 12 inches unit. In other words, 1/4 per foot slope. That's a requirement in IBC. There's one exception, which is shown on the slide, and that's for coal tar built-up roofs. I am personally not sure why that's the case. I can only surmise it's because the coal tar roof is very slippery and the water kind of runs off nicely, but I don't know that for sure. But remember, roofs shall have a design slope of 1/4 on 12. International Building Code goes on to say susceptible bays of roofs shall be evaluated for ponding instability in accordance with ASCE 7. It also says in IBC that each portion of the roof shall be designed to sustain the load of rainwater that will accumulate on it if the primary drainage system is blocked, plus the water that would rise above the inlet. And they give the equation shown there as 16-36 that the rain load is 5.2 times ds plus dh, where dh is the depth of the water on the undeflected roof above the inlet of the secondary drainage, and d sub s is again on the undeflected roof up to the inlet when the primary drainage is blocked. So one is the head, the hydraulic head, and the other is up to the drain inlet. and that's the rain load. Notice that this is being checked for an undeflected roof. Mark will later show some of the load factors associated with IBC and what we think is appropriate at SJI. IBC also says that susceptible bays shall be evaluated in accordance with ASCE 7. There's a section on controlled drainage. I don't know personally how many roofs are being designed today as controlled drainage roofs, but I know that in the 70s and 80s, there were a lot of municipalities that purposely undersized drains and let the water accumulate on the roof so as not to overtax the sewer system. And the big problem there was if the structural engineer didn't know that's what was going on, you may have 6 inches or more of water on the roof, and certainly it was a major load. But like I say, I don't know how much of that's going on today, but you need to make sure. I guess this is a key point. You need to make sure what's going on with the person designing the scuppers and the secondary drainage system. Now, ASCE 7 says susceptible bays shall be designed to preclude ponding instability. It also says roof deflections caused by the full snow loads shall be evaluated when determining the likelihood of ponding instability. Through the years, that has changed. At some points, it was 1/4 of snow, half snow, 3/4 snow, but ASCE 7 specifically says you must check for full snow loads. What is a susceptible bay in accordance with ASCE 7? If any of the 4 items shown here exist, then you have a susceptible bay, and they say you must check for ponding instability. Again, first bullet point, or number 1, bays with a roof slope less than 1/4 on 12 when the secondary members are perpendicular to the free draining edge. In other words, joists running perpendicular to the free draining edge. Bays with a roof slope less than 1 in 12 when the secondary members are parallel to the free draining edge. And then there's some stiffness kind of requirements with span ratio, secondary members greater than 16. Again, indicating item 4 that the roof drains need to be considered blocked. They also show a picture in ASCE 7. What's a susceptible bay? Let's see if I go over here. Here's the susceptible bay, because there's a wall and there's obviously a parapet. Here's an interior condition, so it's a susceptible bay. And this one's not, because it's free draining and it has a good slope. And then there's another picture here based on the slope of the building and scuppers, whether it's a susceptible bay or not. Many of you are used to dealing with FM Global. Basically, many building owners, in order to get their best insurance, have to comply with FM Global requirements. And FM Global has several issues or several comments regarding ponded. I think 2 of the major ones I've shown here in items C and D. Again, when designing and sizing the secondary drainage system, overflow drains or scuppers, assume the primary drains are 100% blocked and cannot flow water. Ensure in item D that the inlet elevation of overflow drains and the invert elevation, and they have some sketches, of the overflow scuppers are not less than 2 inches nor more than 3 inches above the low point of the roof surface, unless you do a very special analysis, which goes on to say. I think the 2 inches is required because you don't want the scupper, let's say, right at the exact roof elevation, because it's more than likely when somebody puts down a tar and gravel roof, for example, they'll encroach on the scupper, and you may not have a opening as large as you think you have. So they kind of wanted to get it up off the surface of the roof, and then they say not more than 3 inches. Actually, the current FM Global says 4 inches instead of 3, but when I was studying this, I saw they had an inconsistency, and I talked with FM Global folks, and they said, yes, definitely it should have been 3 inches, and not one of their publications says 4. So remember the 3 inches. Now, most of you are quite familiar, I would assume, with the AISC specifications, section B3. You know, section B3 in the specs is all the charging language. It's all the you shall do this and you shall do that kind of things. And in B3.10 says design for ponding. The roof system shall be investigated through structural analysis to ensure strength and stability under ponding conditions, unless it's configured to prevent accumulation of water. And methods of evaluating stability and strength are provided in the Appendix 2. Appendix 2 has two ways of looking at the ponding. Section 2.1 is called the simplified design for ponding, and 2.2 they call improved design for ponding. It's a little more accurate, you might say. And you can check either one of those. Typically, what I found in my designs was that when I checked the majority of roofs using section 2.1, they seldom complied with the ponding requirements unless they were over-designed by quite a bit. And so I would often have to go to the improved design method for ponding. And you might recall the improved method makes use of graphs, and you go into the graphs and determine whether your roof is susceptible for ponding. This is the simplified, says that if the C sub P plus 0.9 C sub S is less than 0.25, all is well, ponding isn't. I added this little comment that just popped up on the slide that's not on your PDF of the presentation, just to remind you that C sub P is a function of the span, the secondary span, and the primary span to the fourth, and moment of inertia of the primary members. And C sub S is span of the deck, that's S, and the secondary span of the joists to the fourth, and then the moment of inertia. That's all in the AISC Appendix 2, however. The improved design method, you probably recall that you calculate these values of U, which are a function of the steel yield and the stress at incipient ponding. In other words, the stress, let's say, from impounded water, or the stress from full snow load. And AISC basically allows the strength to go up to, or stress level to go up to 0.8 FY for ponding calculations. And here's just a slide that shows the UP and US and those functions that must be arrived at. AISC, it's important to kind of know what assumptions they make. One is the framing is flat. So there's no pitch on the roof. Members are not cambered. Tapered insulation is not considered. Bays are rectangular. Any adjacent bays are identical. All beams are uniformly spaced. All beams have equal stiffness. Everything's simply supported. There's no axial load, so there's no bending plus axial. And that the water load covers the entire base. So those are basic ponding assumptions used in Appendix 2. Just some strategies. These are pretty simplistic, but provide roof systems to avoid ponding by sloping roof members or by use of tapered insulation to slope the roof. Stiffen the roof structural members by selecting low flexibility constants from Appendix 2. Basically, ponding instability is first of all a stiffness requirement. So the stiffer your members, the less likely for ponding instability. Or you conduct the more exact analysis for ponding following the procedures in Appendix 2. You can use camber, which would also aid in reducing the likelihood of ponding instability. When the last bullet point here, when designing roofs for low slopes, and low slopes I think mean like a 1/4 on 12 typically, parallel joists with end supports at different elevations are more economical in providing pitch into the top chords. So I would slope the member rather than making a joist with a pitch in it. SJI simply says that ponding investigation shall be performed by the specifying professional. Sort of a summary here. All roofs require a secondary drainage system. All roofs must be designed for impounded water per IBC based on the primary drains being blocked. Impounded water heights are to include the hydraulic head above the secondary drainage system. And ponding instability checks are to be made using the larger of snow load or rain load, i.e. the impounded water. I didn't cite it, but don't forget that roofs with snow loads, according to IBC of 20 PSF or less, you have to add an additional 5 PSF rain. And don't forget about the slope of a 1/4 on 12. A couple of slides that I just want to point out. I took this picture a couple of years ago from a window in a building looking down at a lower roof. I don't know how big the tree got in that roof drain, but obviously owners must keep the drains free from debris. Quite often you'll find plastic bags around drains because roofers will go up and not clean off the roof when they've done some work. So just a warning about maintenance. Also, I've seen at least 3 instances where when you have a membrane roof system, what the installers do, they'll put the membrane down and then they'll take the drain unit, fasten it down through the membrane to the deck, and then they'll cut the hole in the membrane for the inlet. Well, if you have an 8-inch drain, it's assumed they have an 8-inch hole. And this particular building had a 3-inch hole in it because they didn't cut the membrane out to the perimeter of the pipe. And I've seen that 3 times. So if you're ever up on a roof and you take a peek down some of the drains, you should see an opening equal to the size that was anticipated. This was another ponding situation I looked at, and it caused me to look at this kind of scenario, of which now there's a picture in ASCE 7. Water coming down the slope doesn't want to go in these drains particularly. It's much easier for the water to come around here and go down here. So this drain gets overloaded very quickly. So I just caution you, because some of our plumbing friends, I'm not sure, recognize this yet, that this situation is going to occur, and you should have a great big scupper here. Okay, a few words about the analysis tool before Mark gets into it relative to ponding. This tool was actually developed in 2016, and I apologize. The slides shows the 2017 webinar series. The new web for SJI says has the 2018 webinar series, so you can check that out. But if you go to Design Tools and click on there, you will find the Roof Bay Analysis tool. And there's several tabs in the tool. This has been around, like I say, for 2 years now. I find it a really useful tool for optimizing joist layout and joist girders layouts on interior bays or exterior bays. And then we decided, oh, gee, it'd be great if this tool also checked ponding. So that's been added. But this general information tab, which is pointed out by the red arrow, just has general information about the tool itself. For example, that the input areas or cells are all highlighted in yellow, so you know that's where you must do input. You can use ASD or LRFD, either way, and there's a pull-down menu that says, okay, you want to design using LRFD or you want to design using ASD. Then there's also on the general information tab a bunch of notes that simply defines what's done in the tool. I might add that when you look at TD3, you'll find a lot more information than even what's in the general information tab. But you know, things like the governing code, how base sizes are limited, joist girder load tables. So don't try to use something that's not in the SJI load tables. The deck stuff information comes from the Steel Deck Institute tables, and deck deflections are based on requirements of the Steel Deck Institute. Bearing length are assumed, minimum SDI bearing lengths. And joist size selected from minimum weight and deflection limits from SJI tables, and some information on the DLH joist. There's more than that, but I just selected a few. There's the picture of the when you go into the analysis tool to actually run it, you'll see that where I have the arrow, we've selected an ASD design, and that's a pull down where you could go LRFD or not. The information in yellow above that arrow is whatever you want to put in is the project name, the project number, who the engineer is, and the date of the work. And then the typical interior bay is the joist span here is 30 feet and the girder span is 50. And there's a little picture. This picture does not adjust itself for the number of joists, but it's there just to show you what the girder span is and the joist span. So you can kind of see what's going on. Something that's been added in our new version that includes the ponding is in version 3. We've added a load called collateral load, which is mechanical and electrical and whatever else you want to put in there. Before that, you had to kind of fudge it into the roofing material. So this is better for checking with certain collateral loads. So that's the load input. You can see roofing material, deck, joist, bridging, etc. You can select your deck, intermediate rib, wide rib, deep rib. The deck profiling gauge, we still say gauge, is this is a wide rib 22 gauge selected. Again, it's a pull down menu. The number of joist spaces on the joist girder defines the span of the deck. So in this case, with the 50-foot with the wide rib 22, the deck span 6 1/4 feet, and the maximum depth span or deck span is 6.92 per SDI requirements. And it checks the moment and the moment interaction for that particular deck. When it gets to the joist girder information, we provide minimum values, default values for the depth or the span lengths, I should say. And also you can override these, not the minimum, but let's say you wanted a 18-inch joist. You could put 18 in here, and you could put as a maximum 18 inches. You'll get an 18-inch joist if it works. And same sort of information for the joist girder. And then there's the deflection criteria, whatever you want. Right now we've got 240. We also have a tab where you can say you don't want X bridging. You want only horizontal bridging if possible. And my joist friends like that, because typically if you can find a joist that only requires horizontal bridging, even though it's a little heavier than one that needs X bridging, it's probably more economical once installed. The new thing at the bottom here is for the ponding application. Once Mark gets in discussing that, you can input any joist load you want or any joist girdle panel point load, and it'll calculate the stiffnesses which are used in the ponding analysis that Mark developed. Also, there's a joist summary. This particular example said it needed an 18K3. Here's the required load. There's the available load. Checks deflections. Does the bridging, because we said horizontal bridging only, so it ends up 3 rows. The length of the bridging. Same for joist girder. It got a 52-inch deep girder, a joist spacing, etc. So you can play with this and you can really get an optimum design. One thing that's in there is costs. And you can get these from the joist manufacturer, deck manufacturer, general contractors, erectors. These were numbers I obtained like a year ago. This was the price of deck per ton. So you don't have to just go by weight if you want. You can see that the installation of X bridging is $3.50 per foot, whereas horizontal bridging is $2. So you can update that from whoever you are in good graces with, and we'll give you some of their rough numbers. Once the analysis is complete, it'll give you the total cost and weight results, as you see down here. And this is per bay. So you can fool with it and see what's the least cost. Once you arrive at the solution you like, you can say copy to the table, and there's a table that has 8 runs in it, and you can get a summary here, and this way you can do a bunch of runs and then compare the costs and the weights as required. So I didn't do any of the ponding stuff. That's what Mark's going to do.
Jim gave an overview of what the requirements and building codes are related to ponding, including the AISC Appendix 2 procedure to evaluate susceptible bays for ponding. He also introduced you to that really nice tool, the SJI Roof Bay Analysis tool. So I'm going to continue the presentation by introducing a new method to evaluate susceptible bays, as well as its implementation within that Roof Bay Analysis tool. But before I go into detail about the new methodology, I'd like to talk about the motivation for its development. The method of evaluation described in AISC Appendix 2 is widely used, but as Jim mentioned, it was developed for cases that satisfy a fairly lengthy and restrictive set of assumptions. I note a couple of those here. and this might actually speak to the question as well. The AISC Appendix 2 method assumes a perfectly flat roof. That means no roof slope and no camber, both of which can be beneficial in resisting ponding. So for instance, even with the minimum roof slopes, ponded water can be limited to covering only a portion of the bay, as opposed to covering the whole bay, as is assumed in the AISC Appendix 2 methods. The AISC Appendix 2 method check is only a check against maximum bending moment in the primary and secondary members. Now, this is appropriate for the structural steel framing that satisfies the assumptions of the methodology, but it isn't appropriate for open web steel joist roofs where the bending moment and shear strength vary along the length, and local checks can control too. Also, the AISC Appendix 2 methodology only works under what's basically ASD level loads, not LRFD. So this isn't the biggest limitation, but it hints that there's something about the method that is different than the other aspects of stability design that we typically deal with. And really, it shouldn't be that way. Typical design for stability accounts for geometric nonlinearities, P delta effects, and material nonlinearities, such as inelasticity caused by yielding. Ponding, the reason it's different is that the nonlinearity is in the applied load. But there's no reason we can't treat this nonlinearity in the load the same way as we treat these other types of nonlinearity. And that's the main idea behind the new method to evaluate roof ponding that Jim and I developed and is described in the SJI Technical Digest 3. This new method is called the Direct Analysis Method for Ponding, which has we think, a nice acronym, DAMP. It has this name, Direct Analysis Method, because the load effects due to impounded water are computed directly based on the deformed shape of the roof. However, it really shouldn't be confused with the direct analysis method described within Chapter C of the AISC specification. For example, there's no 0.8 stiffness reduction. Similar name comes from the fact that they are similar in concept. The similarities lie in the fact that we're using a more advanced analysis capability to capture within the required strength what used to be captured in the available strength. In the Appendix 2 method for ponding, like Jim just went over, the stress indices are computed based on a linear analysis of rain or snow loads on the undeformed roof, a pretty simple analysis. And then those indices are compared against limitations that include the flexibility of the roof. In the direct analysis for ponding, that roof flexibility is incorporated in the required strengths by performing a fancier analysis. And the comparison to available strengths is a comparison that would look very familiar if you were doing any sort of other load. So to account for the roof flexibility in this method, the required strengths are determined from an analysis that captures loading from the impounded water on the deformed roof. This is not an easy analysis, and there are very few software packages that can perform this sort of thing without a lot of help from the user. There are closed form solutions that are available for simple cases like individual beams. But more general cases require the use of iterative analyses to converge upon a solution. But beyond this requirement to capture the nonlinear load, you don't need to have anything else fancy. So it doesn't need geometric nonlinearity, second order effects, or any sort of inelasticity. A simple linear elastic model would be sufficient. When you're performing this analysis, SJI recommends the following load combinations be used for the ponding instability check. Dead plus 0.75 P, which is the impounded water load, plus 0.75 snow. That's for ASD. And for LRFD, you would use 1.2 dead plus 1.2 impounded water plus 1.2 snow. There are a few things to note about these load combinations. First, I said SJI recommends these combinations. There's no code requirement for specifically how to check ponding instability. and thus there is some flexibility given to the design professional. Second, in these combinations, water and snow load are acting together. This is different than what you would see in the IBC strength combinations. And it's based on a situation of a rainstorm coming along after a snowstorm, or snow melt from other bays traveling to a susceptible bay where the snow hasn't started to melt yet. And the third point I wanted to make was that because we have these lower load factors, the 0.75 on the water for ASD as opposed to 1.0, these are only applicable to the ponding instability check, and the IBC strength combinations still need to be checked for strength. Now, we believe at SJI in these recommended combinations, the reason that the factors are lower is because of the lower uncertainty of this case. Water has a pretty well-defined density, and we're computing the actual volume of water directly. So there's quite a bit less uncertainty involved in this evaluation than other typical evaluations. These are recommended load combinations, and they're good for this new methodology. ASCE 7 or the IBC might clarify some of these in their future editions. So noting, again, that the analyses are nonlinear, SJI further recommends that we use the force level adjustment factor from the AISC specification. This is based on the requirement in Chapter C that all load-dependent effects shall be calculated at a level of loading corresponding to LRFD load combinations, or 1.6 times ASD load combinations. So what this means is if you're using ASD, all the loads should be bumped up by 1.6 before you run the analysis. You run the analysis and divide all of your results by 1.6. This ensures that the level of nonlinearity is equivalent between the two different methods of design. Given that the snow and water are acting at the same time in these load combinations, and that these two loads represent physical quantities of material, it does make some sense to account for the overlap. The density of water only is 62.4 pounds per cubic foot. The density of snow only can be estimated as somewhere between 14 and 30 pounds per cubic foot based on an equation in ASCE 7. And it's fine to take the density of water and snow, the slushy combination there, the overlap, as the maximum of these two densities, the water, rather than the sum. And this special accounting for the overlap adds a little bit of complication, and it isn't required, but it does help to reduce the load a little bit. So the required strengths are obtained as shear and moment diagrams from analyses that satisfy the requirements that I just went over. These moment and shear diagrams are then compared to the available strengths in the form of shear and moment envelopes. Here are the shear and moment envelopes for a joist. The moment envelope is a parabola with maximum load, maximum value of WL squared over 8, W being the specified load capacity of the joist in either ASD or LRFD. The shear envelope is multilinear based upon the shear diagram for that same beam. A minimum of 25% the end reaction is given in the SJI specification. However, no shear reversal strength is given in the SJI specification for joists. I show an assumed 12.5% of the end reaction as shear reversal strength. This is the assumption made in the SJI roof bay analysis tool, but it's important to note that action must be taken by the design professional to ensure this capacity. Beyond the moment and shear diagrams, the interaction strength of the top chord for axial load and bending between the panel points should also be considered as an available strength limit. Here are the shear and moment envelopes for a joist girder. This one has 8 spaces. The moment envelope is multilinear based upon the moment diagram for a simply supported beam with equal point loads. The shear envelope is also multilinear. based upon the shear diagram for that same beam. A minimum of 25% of the end reaction is given in the SJI specifications, and 25% of the envelope is permitted for shear reversals in the opposite direction per the SJI specification. So this methodology that I've described, the direct analysis method for ponding, is intended to be applicable to a real wide range of cases, really a general methodology. An implementation of it has been made in the SJI roof bay analysis tool for a specific range of cases. Here's the screenshot of the opening tab of the SJI roof bay analysis tool, and new in version 3.0 are 3 tabs. The ponding instructions, which has notes and other information specific to the ponding analysis. The ponding analysis tab, which was where all the calculations take place. And the ponding load results tab, which has a copy of some of the output. And it has a copy so you can have it allows for a wide table to be nicely printed. Just as with the other parts of the roof bay analysis tool, you're only investigating one bay at a time, and the bay is limited to be rectangular with equal spaced and equal sized joists. Within the ponding analysis tab, the input is split into 2 categories. The first category, general input, include basic things like the bay widths, the selected joist and joist girder, and the dead and snow loads. Each of these things is defined or computed on the roof bay analysis tab and copied here automatically. But that roof bay analysis tab doesn't address everything necessary to perform the ponding analysis. Thus, we have additional input that needs to be given in this ponding specific input section. Here, you define the water level. You're given the option whether you want to compute the water load on the deformed roof or not. Yes, for the ponding analysis. No, if you are assessing rain load as defined by ASCE 7 on the undeformed roof. The SJI recommended load factors and force level modification factor are given as default with the option to override to a different value. The top of roof elevation is given at each of the 4 corners of the bay. It doesn't really matter what the datum is that you use here, as long as it's the same that you use to define the water level. Camber for the joists and joist girders is defaulted to those given in the SJI specification, although you are given the option to override them. And then there's a series of yes/no switches to define the adjacent bays. Yes means that there is an adjacent bay and it's mirrored from the current bay, and no means that there's a free edge. So this doesn't really cover every case, but these 2 options can approximate a fairly wide range of cases. You can define the joist supports to be walls instead of joist girders, which then assumes that they're rigid. The edge joists can also be defined as rigid in case they correspond with a wall. And then finally, the effective moment of inertia of the joists and joist girders are computed and taken as the default, but an option is given to override these particular values. So once all that input is defined, the only thing you need to do is click the Run Analysis button. This triggers a macro, which runs in the background and does all the heavy lifting. It is an iterative analysis, so a loop is performed until convergence is found. In each time we go through the loop, the ponded water loads are computed based on the current deformed shape of the roof. Then with those loads, each joist and joist girder is analyzed. The reactions for the joists are the applied loads on the joist girder. And after the analysis is finished, convergence is checked by seeing how much the water load has changed from the previous step. Once convergence is reached, moments, shears, and other results are computed and displayed back on the ponding analysis tab. The one bit of data that is updated during the analysis is the total water load for each iteration, as shown in the figure here. The analysis typically takes only a second or two, so you probably won't be staring at this while you're running the analysis, but it provides helpful information. For example, if you have an unstable bay, you will see the total water load continually climbing with each iteration, not converging to a single value, as shown here. A quick note on the computation of the water load. The bay is discretized into a grid of cells, and then equations are used. And these equations come from a journal paper from the Journal of Constructional Steel Research to convert that volume of water into a set of 4-point loads. And that's done at each one of the grids, each one of the cells within the grid. For the roof bay analysis tool, the grid has 20 cells along the direction of the joist, and the number of joist spaces is the number of cells in the direction of the joist girder. The ponding analysis tab has several results tables. Here is the joist output table. For each of the joists, the maximum shear, the maximum moment are shown, along with equivalent loads. The equivalent load is the magnitude of a uniformly distributed load whose moment or shear envelope completely encompasses the computed diagrams. Another way to think about this is that the equivalent load divided by the specified load capacity from the SJI load tables is the maximum strength ratio along the length of the joist. That strength ratio is also listed in the table, as well as an indicator to show if it's greater than 1 or less than 1. Less than 1 meaning sufficient strength is provided, more than 1 indicating an overstress. Additional joist results are shown in this table. These are the magnitudes of the distributed load as a function of length along the joists for each of the joists. 20 different points are given along the length of each joist. This data helps you make more sense of the physical behavior. More load is going to be wherever that water is the deepest, but it also allows for a check against local overstressing. Ponding causes non-uniform loads. There can be situations where the moment and shear envelope checks pass, but the applied loads on one portion of the joist are greater than the specified capacity. This can potentially cause a bending overstress in the top chord. Total loads greater than the specified load capacity are highlighted in yellow and red, which also gives a nice visualization of where the water is the deepest on this ponded roof. This is similar to that previous table, but it shows the total distributed load in excess of the allowable load. This is the extra load that you have to figure out what to do with. And it's really left to the design professional what to do with these potential overloads. In this example, the overload is fairly light, 28 PSF or pounds per foot versus it was 200 and some on the previous slide is the capacity. But this also occurs at the joist ends, where the axial load in the top chord is less. So potentially that these overloads don't really cause an overstress. However, if they get large, it's probably best to select the larger joist. Joist girder output is shown in this table. For this example, the top joist support was defined as a wall, so no results are given, other than just the joist reaction. The bottom joist support is a joist girder, and the bay was assumed to be mirrored. So each panel point load is twice the joist reaction plus the weight of the joist girder. Panel point loads larger than the allowable load indicated in the joist girder designation are highlighted in yellow and red, and a strength ratio based on the shear and moment envelopes is given. So now that I've described the new method and its implementation within the SJI roof bay analysis tool, I'll go over the general procedure for its use. First, a preliminary design of the roof must take place, selecting things like roof slopes and the location and type of drainage systems. From this information, you need to identify which of the bays are susceptible. Each unique susceptible bay will need to be checked. Then you perform a preliminary structural design to get trial joist and joist girder sizes. The Roof Bay Analysis tab is quite helpful for this. To get the water level, we need the hydraulic head, which is based on the flow rate, and all of that is described in the commentary to Chapter 8 of ASCE 7. The water level is determined as the hydraulic head above the secondary drainage system. There are some code requirements for the relative height of the drainage systems, which the roof should conform to as necessary. Next, you need to input all the required data, including your freshly calculated water level, into the ponding analysis spreadsheet. Then run the analysis. If stability is achieved and all stress ratios are less than 1, your bay is deemed sufficient. If not, you'll need to stiffen or strengthen the bay. You can reduce the joist spacing or specify a larger joist or joist girder. To increase the joist or joist girder size, increased loads can be entered into the optional increased load data table that was added in version 3.0 of the spreadsheet. As I mentioned before, you can run into cases where the moment and shear envelope checks pass, but you have some applied loads higher than the specified allowable load. In these cases, the design professional will need to determine by analysis or by judgment if the overloads are okay or whether larger joists and joist girders are needed. So with that, I'd just like to make a few concluding remarks. In this presentation, we've given an overview of some of the design provisions related to ponding, including the methodology of assessment in Appendix 2 of the AISC Specification. We've identified several limitations of that commonly used methodology, especially for open web steel joist roofs. We introduced a new method for ponding assessment, its implementation within the SJI Roof Bay Analysis tool, and a couple of examples illustrating its use. I suspect this has been a bit of a whirlwind of information, so I recommend checking out the recently updated SJI Technical Digest 3, which Jim had shown, on ponding, which contains what we've talked about today, plus additional background, examples, and information.